for everybody. So thank you for having me in this National Training Week event. As I understand, this is more like an introduction to the training that we have been giving as well. So I don't think we can achieve much in this 1 hour session. Yeah. So just like I will give you I'll just walk you an example. No more theory, just an example on where to find the software, and then how to start with that, and then we will then go through the typical steps that we do for analytics data in terms of we explore data, exploratory data analytics, and then how we make the model from the data, what people know as predictive analytics. And then lastly, we would discuss on, okay, now we have the model. So how we use the model to tell us what to do, which is the prescriptive analytics, which is the last step. Um, Give me 1 second. Um, I'll share my screen. Yeah, so what I've done is basically you can just go through, yeah, because we have very limited amount of time anyway. Um, and then we have a lot to cover. So I think most of us have seen this type of graph. Uh, so we have on the x-axis is then the value, and then on the y-axis then what they call it sophistication, but I would say it's more like more effort needed. And then these are on the think yeah what we have as in the descriptive, what I said before. So we have a bunch of data, and then how do we make sense of that data? And it's just like more, if we think of it like a Lego blocks, right? So if Lego blocks, and then we have like a box of Lego blocks, and then we try to like segregate different shapes and then different colors so that we can see and understand where things are. And then with that, we can describe, okay, so this unit of blocks is going to be used for that part, and then this one is for the other part, and so on and so forth. So that's we have the data, and then we describe, and then from that data, we analyze it, and then we describe what has happened. And then the next step is then it gives more value, because then we can then predict, okay, if I have this sort of inputs, what could be the outcome that I can anticipate or I expect. So we will need another effort to do so. So we are going to use the model that we understood already to make it into a model, which then it will bring more value as shown in this diagram. And then that I can move, right? The inputs that I can move, or the X variables that I can move, or the independent variables that I can move. I want, if I say I want to like maximize my profit, for example, which handles or which inputs or which independent variables that I need to move, right? So in the in the process industries, like in oil and gas, chemicals, petrochemicals, food industries, all things that process by nature. So we would see that as okay, which valve that we need to open or close in such a way that we can maximize it. So in this example, we are going to work with a very simple data set that I've been using so far. So we have, I think I can just simply open this guy. Right, so if there is any question, just type in on the chat, and then Jalif can then let me know if there's a question. Yeah. So I have this list of data. We have a meal type, like breakfast, snack, morning, lunch, dinner, late snack, and then another breakfast for the next day. And then we have the items. So, okay, what type of foods that are available for the breakfast time? And then is this honey, for example, is this under sugar category, right? For the food category, it's under sugar. And then this honey, it contains no fat, but a significant amount of calorie as we know it, and then some hydrocarbons, and then zero protein. And then this is then some imaginary price. I'll show you later why we need this price anyway. But then for sure we will need that price because we are going to maximize profit or minimize cost in a way. So we have I think we have we have about 300 data points, and then the question is then, okay, now that's the most important one, right? So if we have now a bunch of data, what is the question? So if I see this, right, so all of us can think of what type of questions that we want to ask ourselves when we see a data. So if I see this, for example, okay, can I see, for example, what are the distributions of these items, right? So and then how many honeys or items is being used during lunchtime or dinner or breakfast. And then if you want to know, if you want to be like a bit engineering in a sense, then okay, which food that has the highest content of fat, for example, or the other way, I mean, similarly, what type of food or which item that has the highest calorie or the lowest calorie, and carbohydrate and protein and so on. And then, but at the end of the day, okay, so if I want to, like, for example, predict, can I predict and if I know this food and that food and that food, if I choose this for eating without looking at this table, can I then say, okay, I have eaten this amount of calorie, knowing the fat, the carbohydrate, and then the protein content of these three foods. So we could also do that, right? And then once we know, okay, if we eat a certain amount of foods, right, and then this is like one item means like one portion, yeah, we can safely make that assumption. So one portion. So if we items, if we don't know what the calorie is, we can then use a prediction to calculate what the calorie is depending on the fat, carbohydrates, and protein. And then once we get that model, we can then using the same data sets, we can then see, okay, if I want to minimize my cost, and then I need to have a certain amount of calories per day. I need to have per meal, and I want to have a certain carbohydrates per meal. So which type of food, which item that I need to consume, right? So I've been like maybe I'm too fast to let me know. But it's just like giving you a hint on what we could do. Yeah, what we could do. Again, we will then do this like straight to how to use Python in this case to do this thing. So there are many. Python is like an open source software, right? So which we can download, and then I normally use Anaconda platform. So for those for those of you who don't know it yet, we can just simply Google Anaconda download, and then we'll go to this download Anaconda. And then in this Anaconda download, we can you can put an email address, and then they will give you a bunch of stuff. And or we can also skip registration, and we go to the download for the whole package of Anaconda, or they say a mini conda. So it's a smaller type of conda download, and then install it. So once we install it, I think we have something like Anaconda. So we have this Jupyter notebook, which I am now opening. Or we could also have something like, let me see, sorry, that one, which I wanted to show you. So, so these two things that I normally use. So the Jupyter notebook, the one that I am going to use in this demonstration, and then the other one is then the Spider. So this Spider, it looks a lot like other engineering tools, like if you are familiar with MATLAB, so it has a feel and look like MATLAB. So I'm using these two tools from Anaconda platform. I just go to download Anaconda. It's free, and then you skip the registration and then go to this download and then install it. So right now So I don't think I can then yeah, because I cannot monitor in you again. Yeah, I mean this is just an introduction. If we want to have more detailed discussions and in-depth training, we can then discuss it with IEM or with me later on. Um, so quickly, typically in industrial problems, we have three steps, right, for data analytics, and then in most cases, well, in my limited experience, majority of the case that we see is basically we're still struggling in the exploratory data analysis step, which is a very basic one. Which is a very basic one. Why is this very difficult? Because we don't normally have this in our traditional engineering curriculum. We don't have this in-depth thought. So we leave it to the industries, to the companies to train the engineers to do so. So that's the something that we need to improve in the future. So nonetheless, so how to do this? So once we open that Jupyter notebook, we will get something like this, and then we can create new Python file, right? And then it will give us the another page, blank page, and then which I already see a blank page like this, and then I already create my own notes, so we can just simply go through this. Um, so the first one is to do descriptive analysis, to describe the data, right? So from the data, we need to know what is in there. So typical stuff that I do, right? So in Python, because it's open source, many people, they have developed their own code, and then they package that so that other people can use and improve. So that's the strength of the open source platform. Um, in this case, we are going to use a package called pandas. So the way we write it is that we type import, and then type pandas space and then SPD. So this is just like an abbreviation. We also don't have to do this. Import pandas done, or we can just simply import pandas SPD like normal people would do, right? In this Python community. So and then we shift enter, and then it will run. So you can see it was star, and then it has imported pandas as PD. Um, and then after we import the Python package that we need, so we are going to read the data that I just showed you, this data into this guy, into um uh, um uh, this code basically. So how to get this data in? So once we have it in Excel, we open that Jupyter notebook. We come to this page, right? In your case, maybe if you haven't used this, it will be like an empty page. But then you can then click here, upload, right? Upload. So upload, click this upload, and then you simply upload the data, and then you'll get your data in here. I think this one, food basis with price. So this is the data that that we have here. So food basis with price. So once we upload it to this platform, this is by the way in our folder, yeah, in our Windows Explorer in user. Thinking it sits in our computer. And then once we upload that, and then we can just simply define a name like dataset. So this is what most people do again, but you can use your name or whatever. So dataset equals to PD. We type PD and then the dot and then read underscore Excel. So this is basically the language that people use in this package to read Excel file. So we read Excel file, open brackets, and then we type in the name of the file. We type in the name of the file. Once we type name of the file, and then we can then shift enter. So once we shift enter, we need to check whether it is there or not, right? So for example, so if I want to see, what is in there. So we just simply print, and then the open brackets, and then type in the name that we give it here. So for example, if we have this like a data one, for example, or my data, right? Just to give you a quick, and then enter, shift enter or control enter, and then now I have my data. So this is then my data, prints my data, and then we control enter, and then we get to this the data set, and then we can see we can compare if this is really the case. Now if I sorry right, so to quickly see, we have row number 0 is then breakfast. And then the headline is then meal item, food category, and fat. So Python in a way it's very good. It can then detect the headings, and then it will then start at row number 2. Python starts with 0. Don't ask me why. It's just their language. So it will then start with 0. So row 0 is the breakfast, right? Breakfast, and then the item is honey, and then the food category is sugar, right? Food category is sugar, and then the fat of this guy is 0. And then the next column is that you can see calories is 21. Calories 21, right? Still row 0. Still row 0. Carbohydrates 6. And then protein 0. And then the price is zero point 0.4. Price is zero point 0.4. Right? And then what's interesting about this print data, we get the top 5 and then the last 5. And then we can also compare the last 5, but I think it should be okay, yeah. And then once we go, once we get our data in, now we want to do some exploratory data analytics, right? In this case, we're going to do the engineering term. So we're going to use only the numbers. So the calories, carbohydrates, fat, protein, and then the price, because these are the numbers. Now my data is then, it's not no longer data set, but my data. Right, so I name it like a data numeric. So I only want to see the numerical part of the data because we have all of this what they call it uh, uh, strings, right? And then I want to see only data. So this is my data, and then this is how we write it in the column into column. So we have this square bracket and then another square bracket, and then calories, carbohydrate, fat, protein, and then price. So these will make, if we do it this way, it will make it into like a columns like this. So if I do this, right, and then if I then um, uh, describe, so data numeric dot describe, right? So that means I want to describe it using the pandas package. And then name it like EDA, right? EDA equals to data numeric, which is this guy, the whole bunch of columns. And then I want to have the pandas to describe it for me. And then we can then just type it in this manner and then print EDA. We'll get these columns. So this describe is what we know as like the very raw descriptive analytics. What it tells us is for each column, it will count how many rows, which is 303, right? And then the mean value for calories, for example, 72. So we could compare it if we like it. See, if I compare this with Excel, we can see average is 72. So average is 72. So it's basically giving us the same results. It's just like for most of us who are more familiar with Excel and then it's more confident in trusting whether Python is doing its job. So I've been showing you that Python is consistently equivalent to Excel in calculating stuff. So the mean value is 72, and it will then also calculate the standard deviation, right? So well, we'll have another course to explain what this means. But then the minimum is then 0, and then the maximum is 385 for the calories. And then we have the 50 percentiles, the median in this case, and then 25 percentile, and then the 75 percentiles for calories, for carbohydrates, fat, protein, and so on and so forth, right? And then if I this is like a short summary, right? Like a short summary. So if I want to make a histogram, so I can do it this way. So if it's a histogram, data numeric dot hist, right? So this is then how we call it, dot hist, and then we divide it into like 20 bins. 20 bins mean 20 buckets. So if you calculate, this is one bins, this is one bins, and this is one bins, and so on and so on until 20. So from here to there are 20 buckets. And then this is the size of the column, 10 by 10. So these then the calories, carbohydrates, fat, protein, and then price. So we can see them very quickly in using one line, right? So it's a lot more efficient than Excel in this case. So we can see, well, calories is most of the calories they are on this range. The fat is so most of the foods have no fat at all, so we can see the spread out. And then I forgot to notice that in the calories and carbohydrates, there are some like what we call like some data points that are far away from the rest, right? So far away from the rest. These two also far away from the rest. And we can see this data is a little bit so skewed to the left. This guy also skewed to the left. This one is extremely skewed to the left. This one skewed to the left. This is a bit more like yeah, slightly skewed to the left, but it's not as extreme as the others. Now, if you want to see the relationship within these numbers, right? Calories, carbohydrates, fats, protein. I don't think you want to make it into price as well. But nonetheless, if we make a scatter plot, so in this graph we have bins, right? So how many items fall into each bin, and then what's then the price? In here, we can then use what is the relation. You can then see what is then the relationship between one variable with the other variable. So the way to do so is then the PD, that pandas, right? Remember this PD matrix, and then with then this data, the data numeric, the one that we just the one that we just only the numerical data, right? That we selected, because otherwise it will give error. So if we do so, and then we get this. Say for example, how to read this. Need to delete all of this AI tools stuff. Able. So how to read this? So this row is then the one calorie, right? This is carbohydrates. This is fat for the y-axis, right? So if this is the case, if we see this graph, we can see that the y-axis is calorie, and then the x-axis is the one below here, which is the carbohydrates. So we can see carbohydrates as the y-axis, as the x-axis, sorry, and then protein is the y-axis. We can see that they are, well, we can see there are some slight correlation between carbohydrates and then calories, but then the most data are like scattered here. And then if we see, and it will simply follow what this line as well. So this is calories, carbohydrates, fat, protein, and then the price. So we can see there's well, some relationship like this exists, but then the rest they are like really scattered, and then like especially this protein guy. So it's not really insightful basically. But nonetheless, we can see, I mean, all of these comments that I've been telling you, it's we can see that from we only get this comments once we see this plot, right? So this is really helping us on understanding what the data looks like. And then if I want to see the correlation, so what is then the number between if I plot carbohydrates and then price, for example, or carbohydrate and protein, how strength is their correlations? So to do so is that we can just simply for the data dot core and then the open and close brackets, and we can see the correlations like this. So calories to calories, of course, they are very strongly correlated. That's one. Positively correlated, right? So if this calorie goes up by 1 unit, this calorie will go up by 1 unit, which, I mean, it's a no-brainer. But then if we see on the carbohydrate stuff, if these carbohydrates has like 67% to the calories, meaning it is well, there's some limits, but we typically use like 0.5, so 50%. So anything above that, that we say, practically speaking, it has some significant influence. So say, for example, these carbohydrates, it is positively correlated with the calories, right? 67%. So we can explain in statistical term, if I know the carbohydrates of an item, if I know carbohydrates of an item, I can 60% predict what the calorie is, right? So, but the other 23% is something that I don't know. It's something that comes from the fat or the protein or something else that we don't know, that is not visible in the data. We don't have, so that's how we read it, but we don't have the negative number here. So negative means the negative correlations. Say, for example, if I increase carbohydrates, I would then have more calorie. But then if it's negative, if I increase something, and then this calorie will drop, right? So they have this opposite effect. So that's the, if we see any negative numbers. But so far we don't see that, and then we can see it clearly from these numbers. We can make sense of it from the graph, right? So this graph. So if we move to the right, it will also move to the left. Sorry, it goes up, like in this case. So they are in a positive, the other way around, like this, like when I move my mouse over here. So this is then where the gradient is negative. That's why we have the negative correlation. So that's how we see this. And then if we can see that, sorry, if we want to see calories, right? So calories highly depend on the carbohydrates, 67%. And then the second biggest influence, than the fat, 61%, which we will get more calories. If we have fat, we have also like more calories. But then protein is not so much, it's only like 30%. So if we have the cut point of 50%, so we can say, well, we cannot predict calories with protein, let alone with the price. So it doesn't have anything to do with the calories, right? So by looking at these numbers, it makes sense. And then they are consistent with the data that we are seeing in the scatter plot. And then if we want to be like a more fancy, we can make like a heat map like this. So what we do is then we import another package called Seaborn, and then we name it as SN. So that we can then say sn.heatmap. Otherwise, we will then have to write seaborn.heatmap. But then it's basically this heat map is basically putting these numbers into colors, So we can see same numbers. So calories to carbohydrates, it's 67%. Calories to fat, 61%, like in this case. Calories to protein, 30%, and then calories to price is 27%. So that's basically the same numbers, but then we can see which variables quickly, right? Because now we have only very simple examples. If we imagine that we have hundreds of variables, so it's not going to be easy to read through these numbers. So it's easier than to go through with this type of map, right? We can see all of these reds. They are on the positively correlated and then strong. Um, Basically, everything that I have done here in one by one, right? One step at a time. So this sweet face is a package that we can see. I mean, they combine all of these analytics into one page, into HTML page. So if I do this data numeric, we are going to analyze this data numeric and then name it report, right? We analyze the data numeric using this package, right? We analyze the data numeric, that columns, the numbers only with this package, and then we are going to put that into report, and then we're going to show that report into HTML, and then we're going to open the browser. So if we do this, we get we'll then do all of this magic. Let's this numerical magic, and then voila, we get our, well, calories. This is the maximum 385, right? Minimum 0, and then medium 50, average 72. right? Remember that 72 point something. And then it gives more detail like the range, interquartile range, and then standard deviation, and then the variance, and then kurtosis. I mean, kurtosis and skewness, these are the measure of normal distribution. So for normal distributions, these two like they are very close to one, right? So if they are very away from one, if I'm right, they are not normally distributed. As we see it, it's not normally distributed, and then we expect these numbers to be not going to be one, right? Not going to be one. And then we hover over this guy, we get the bigger, we have the bigger how do you call this? Bigger graph, and then which we can then, if we highlight that, we click this, and we get this. Sorry, we get this page. So this is more like we can play around with the bin. So 5 bin, and then 15 bin, and then 30 bins, right? So this is more details, and we can see there are many, about 25% something foods items that have like around 50 calorie something calorie, right? 50 calorie. And then we can see more details over here, most frequent values, most value, largest value. So thinking cases are here, except for the correlation between these. If I click this association, and then we can see the correlation. So relative to the others, meaning it has the strongest correlation between these two, right? Calories and carbohydrates compared to calories to fat, for example, which we know this is 67%, this is 61%. This is not so much, 30% something, 20% something, right? So this is how we and we can see this 4 is like this 4, right? So they are all consistent. It's just like different packages which we can use. So now, so this is how we, or at least how I start exploring data to see which variables are connected to each other. And then we try to make sense of the number, right? That's what's more important. So indeed now there are many packages which they can then create a bunch of stuff. And then but if we don't see what's in it, what's behind it, um how um how things are connected to each other, it's going to be very difficult then to convince other people, well, this is on what we see, if we don't have them visible like this. And then the next step. So once we know, what we know now, the calories are strongly dependent on carbohydrate and fat, and then we know the distributions already, and then they are very much skewed to the left. Now what to do with that? So if I say, okay, now the next question is, so we have to be able to formulate these questions in our mind, right? The next question is that oh, well, maybe ChatGPT can help us. But then, in any case, if I want to see, because we know that there is a correlation between these two to the calories. Now, if I want to see what is then the correlation in a predictive sense. I mean, if I want to make a model. If I want to make a model out of this data, how do we do that? So now we come to the next step, which is then predictive analytics, what they call it, predictive analytics. In the old days, we call it like regression, just simply modeling approach to the modeling. The simplest one is the one that we are going to share now. Why we are going to share the simplest one? Because well, we are limited by time. So and then just more, it is only acting like a teaser, right? So so there's another package to have I mean, to use the modeling package. They call it like scikit-learn, sklearn. And then in this sklearn, we don't import everything, right? To make the computation much more efficient. So remember that in the beginning we import, like, for example, import seaborn as an SSN. So that means we import everything under seaborn, all kinds of stuff, right? Package. So we have the I think they have all of these regressions, and then all kinds of types for regression, and then I think another bunch of stuff that I also don't know. But this is then the typical stuff from scikit-learn that I use, uh, which is then we are going to um, split the data. We're going to split the data. Why do we do so? Because then we will need, because we have only like 300 something data points, we're going to use part of that to build the model, and then the other part, typically 80%, 20%. So 80% is then we are going to use the data to make a model, and then 20% we are going to test the model whether it is aligned with the data that we have, right? So that's why we from the scikit-learn and then model selections, we import only train, test, split. So it's quite one else just put the name. And then we are going to select the X and the Y. X and Y means here it's the X independent, or the handles, or the input, or something that we can fine tune, something that we can independently change, right? So that's the X. And then Y is then the things that are going to be dependent or calculated, right? Or in statistical terms, or now in data science terms, they call it this like features. These features. This is, I don't know what they call this. I don't remember. But anyway, so what we want to see is that we define X as the carbohydrates, protein, and fat, right? We simply put all together. Well, you can argue we can just simply delete this, right? And then I can also delete this, and then because we know that fat doesn't contribute anything at all to the calories, and then we're going to use carbohydrate and protein only, and then the data numeric, right? Data numeric is the sorry, the Y value. The Y value is then the calories. So based on this, using these two variables, we are going to predict what the calorie is, but first we have to define which one is then the, which is this guy. So if I do this, right, so we only have this X and Y, and then if we print the X, right, print the X, we have only carbohydrates and protein, and we print the Y just to make sure that we get it right, right? So we get it right, and then we are going to split then, right? Because we have 300 data points and two data points, we're going to split this into 80% is the training set, and then 20% is the test size, the test set. So we split into like we split the X first into X train and then X test, and then the Y train and Y test. So we're gonna have like four sets of data. And then this X is then this guy. Sorry, we're going to define this into 4 columns, and then these are the column the data that we're going to use. This is the X, this X, and then the Y is in this Y. And then the test size is 20% is going to be used for testing. And then we are left with 80% for data for test, for training, sorry. And then this is just some random step. If we don't have it, we will it will then randomly select which of these 80% data that we are going to use. Otherwise, if we keep a number here, it will then every time we run this, will get the same number. So if we do this, and then we describe the data again to make sure that we get what we want. And then we describe the X, sorry, this is the X describe, right? Because this is the data that we have for training, which is how many? 242. So if this number divided by that 300 something, it should be like 80%. The same thing with the test data. So we get to this. And then I don't think we want to describe the Y, because I think we know it already. And then we build a linear model, because that's very easy to do, right? So we then from the same package we import linear regression. That's what it means. And then how do we know that we are modeling it correctly? So we need to have a metrics like KPI. So from the scikit-learn as well, we import the metrics, which is like mean absolute error. So the difference between the model, the predicted number, with the data, the actual data from Excel. The difference between them in absolute sense, it will then be sum, and then average that to get this MAE, mean absolute error. But we could also say the mean squared error. This is what people mostly do because we are going to um, how to call it, so for example the fat, right? So it's I don't know, the unit of fat, for example kilocalorie, and then the predicted one is kilocalorie, and then the data is also kilocalorie, so both have the same unit. So the difference between them is still using the same unit, right? Kilocalorie. And then we square it to make everything positive, right? And then we find the root, the square root of that, right? We square it and then the square root of that. Basically, we want to just simplify the positive number. And then by squaring it and then square root it, we'll get to the same unit as well. So this is most important, more important compared to this one, but nonetheless, we have everything. And then there's this R2 score. So for linear regressions, we typically use the R square. So that's what we're going to need. So now we have this package, import. Now we name the model like linear regression model, and then we call this guy simply by writing it this way. And then we're going to train the model by using the X train and then the Y train, this guy. So this model, which we have defined as a linear regression, we're going to fit this X train and then Y train, right? And then we can do this in this session. So if I add, if I click A, if I highlight this cell, if I tap A, I get another page, another row here, right? And then I do so, and that means I have this LR model, but we will do this later in step by step. And then this I do, that's one thing. Sorry, one more in another row, and this also another row, and then at the end of the day, I put them all in the same in one cell for easy explanation. And then once we fit the model, we get the model, right? So once we learn from the data what should the linear regression is, and then we are going to predict the or use the model to prediction. So we get the same model, and then we're going to dot predict, and then we are going to use the other data set, the 20% data set, which is the X test, to predict it, right? So we use the model, we call the package, and then we use the training data to make the model in this case. And then once we get the model, we will then use the model to predict the test results. And then we will then compare, by this matrix, right? The matrix that we have for the mean absolute error between the data that we have, right? The Y test, this Y test, the data that we have, compared to the predicted data that we have from here. And then the same goes with the mean square error, and then the same goes with the R square, so that we can see what the numbers are, and then we simply print the matrix. If I do this, right, and then I get this one. So the mean absolute error is 25, and then mean squared error is 1053, same unit as calorie. And then the R square is then the 40%. Well, it's not really good, right? It's only 40%. So because we simply left out the fat, and then we know when we left out the fat, I mean, this guy can only explain 67%. This guy is 61%, and then the fat explain about 30%. So if we have if we had included the fat, we would get more like a more fit model. But nonetheless, this is an example. Right, so 40% of R square, not really good, but okay. Nonetheless, if we know, okay, because this is linear regression, right? If we remember, linear regression is just like simply y equals to mx plus b, or mx plus c, you know. So we have the intercept, the b, and then we have the gradient, the m. Right? So the intercept is, sorry, the gradient is then the coefficients in this scikit language, and then the intercept is simply intercept. And then don't forget to put this underscore, and then we then print them, right? So I used previously the fat was included in the previous example, but now we are going to have protein and then carbohydrate only, or carbohydrate and protein only. So if we do, oh, sorry. This one, right? So the fat is gone, and then the coefficient for the carbohydrate, coefficient for the protein, and sorry, carbon coefficient for carbohydrate, coefficient for fat, and then the intercept. So meaning we have calories equals to 34.8 plus 4.2 times carbohydrates plus 2.2 times fat. So that's basically what it means, right? So now if we want to deploy this into an app, an app, right? We are going to use a Streamlit package, and then we're going to use NumPy as well to do the calculation. And then in this case, we can say, well, calorie prediction app one, for example, version one. And then I can just simply write this is the title, and this is then the description. So we don't use protein, right? An example, we use only carbohydrate and fat. And then the features, right? Or the X values is then the fat carbohydrates is not used. So if I don't use it, we just simply delete this guy. And then, so now the model, now we have the model, and then we can just simply copy this guy. Um, right. This is then the 4.2. This is then this guy. Just simply delete this. And then the intercept is now a different one. And then remember, this is only like 40% accurate, just so you know. And then so now we have this, we add buttons, and then we can then say, okay, carbohydrate, protein, fat. So carbohydrate, protein, and then there is no fat anymore. So I delete the fat. Sorry, I delete the sorry, protein, fat. Right, because we have carbohydrates, and then fat is then the fat, and then so this number belongs to that, this is belong to that, right? So we have to make things consistent. And then the prediction is then we multiply the features, this guy, this fat and carbohydrate, the value that we input, and then we multiply with the coefficients that we defined over here, and then plus the intercept, which is this guy. The intercept is correct, right? And then we write the prediction. And once we do this, um, we save this as a, for example, if I now save it into Python code. So for example, if I have to open I have to create the Python the .py, because this is in Jupyter Notebook. So I have to create this, and then and then I normally create this using Spider. Now I'm showing you the two tools that I use, and I had to create this because we have to create this as a Python package. Sorry, as a Python code, so that then we can call it, because it's now this package works in different way. If I now so n copy that code, right? Same code, I copy this, and then I save it as so I save it here in this um in this Dropbox Python, and then the food exercise food one, for example, I don't know, food one.py. And then I know where that thing is. I changed the location into my Python folder, right? Dropbox Python. And if I go to files, we should be having that food one as the last data. See this one, food one. So this thing, so this code is now saved in my Dropbox folder, Python, and then food1.py. So that's what this file is. And then we just simply yeah, either we copy paste this or we just simply like I do copy absolute path, right? Copy absolute path. So we know. And then the way to run this Streamlit is basically yeah, we save it and then run Streamlit run and then this. So how to run this? Then we search and then we search Anaconda prompt, this guy, because we are using Anaconda prompt, and then we just simply say what is a Streamlit run, right? Streamlit run, and then our location. So in the folder in the drive D Dropbox Python for one, then we enter, and then we get something. Right? So we get this simple app, but this is still in our local drive. So the name is calorie prediction app underscore v1, just like yeah, that's what we write basically. And then it's apps predicts blah blah blah. And then it says okay, now key in the fat and carbohydrates as we fat and carbohydrates, right? Um so if you want to say okay, I want to put like I don't know 10, enter, and then 20, so it's going to be like so fat. If I click then predict, it will then predict me 141.9, right? So say let's take a look. Let's take a look with this one, for example. If I want to use just to make a sanity check, we know that it's not accurate because it's only like a 40% accurate, right? So so if I say cranberry raw, which one is which? Let me uh, view, right? So what was it? Cranberry raw, for example. So no fat, 26 calorie, no fat, and then carbohydrate 7, and then it should predict to us 26 calorie, right? Should be in that order. So let's see. But we know already that our model is not that accurate, only 40%. But we will see how the model thinks if we have zero fat and then 7 calories. So I put like zero fat and then 7 calories, and then predict. So 64, while the data says 26. So we are like over predict this food. But then say for example I want to have like I don't know, mocha or Snickers, right? 5 and 18. 5, enter, 18. And then predict 122. And then we get, what do we get? Come on. 133. Yeah, okay. Not so bad. We under predict the fat, I mean the foods with more calorie, but we over predict foods with less calorie, right? So it's a bit skewed. But well, we know this, and then what needs to be done later is that to make sure that get more data, and then make sure that this data, which I can let you know later, that this data is not really clean, right? So nonetheless, we have a few minutes left. So that's how it looks. And then, so now we can make the model, right? We have done the predictive analysis. Now, so now if we know, or if we can predict the calories from the fats and then carbohydrates, now how do we know? I mean, if we say it comes with a price, right? It comes with a price, meaning like this. So if it comes with a price, so yeah. If we say, well, I want to eat some food with this amount of fat and then that amount of carbohydrates and then with minimized cost. So how do I do so? What type of food can I eat, right? So it's what we call the prescriptive analytics, or what we know is like optimization or mathematical optimization. So how to formulate that? We're going to formulate that in a linear term. We call it linear programming. So the objective function, because we want to minimize the cost. So we're going to multiply um, one meal, this item. If this is one, we multiply this by that, right? So 1 times 0.8. So that would be our cost. And then if we sum all of this, right? Because we don't know how much we want to eat for this. So just item this times that 26.8 times this number, which is a variable, 26.7 times this number, which is a variable, and so on and so forth. And then we sum them. So that's what it means. But there is a constraint, right? Because we say we want to eat a certain amount of foods or combinations of foods that fulfill like a minimum value of fat, right? Because we don't want to, like, if we say minimize cost, it will then say, okay, now you don't have to eat anything because they will then save you a lot of money, right? That's what it says, right? If we say minimize cost. But then we want to minimize cost, but we still want to have something in our belly, basically. So we define minimum carbohydrate. So if we say I multiply this with this carbohydrate, so 1 times this guy plus this 16 times this guy plus 43 times this guy and so on and so forth. If we sum them, we'll have to reach at least a value, minimum carbohydrate. The same goes with the protein, the same goes with fat. And then we also know, okay, well, maybe we will need to limit ourselves, right? Maybe not so much. But okay, we'll see. We'll have this as well as a constraint. So this is what we call the mathematical formulation. This is the objective function that we want to minimize or maximize. In this case, we're going to minimize this. And then these are the constraints or the model itself, which is very simple model, right? Again, this is for teaser and introduction. So how do we do this? So number one, as I've done this before, we know that in this food we have redundancies. So that means it will not, and then redundancies as in like well, the same food, different use different and during different meal time, they have different numbers here for the fat, calories, and protein, and then that confuses the Python. Okay, so now there are like 10 Snicker bars, for example, and then all different numbers. So and then always, well, people complain, which just pick your choice. So I remove the redundancies, and then I am left with I think instead of 300 something, I got like something like, yeah, 132 unique rows, 132 unique rows. So that's what I'm left with. This is something that we need to load. And then again, we check the data, right? And then we add these limits. So I want to eat minimum 500 carbohydrates, 400 proteins, 100 mean fats, and then 1,000 serving, right? So just to make it like I can eat 1,000 portion, for example, just to make it like as relaxed as possible. And then the package that we're going to use is then Pyomo. So Pyomo dot environment, we import everything in this dot environment. And then we then um, the data set is then df, right? df here. So we put the df into the items, these items. Sorry, this item. Where's the item? So this item column as the set, right? So it is the set of food. So this is like a set of food. So if we do this, and then we then define the parameters. So the parameters are basically this number. So this food, what was the food? So almond something. Um, it has 9 fats, 103 calories, and so on and so forth. So that's why how we define the parameters. So the carbohydrate is then the food item, and then what's then the corresponding carbohydrate. The same goes with the protein, the food item, and what's the corresponding protein. And then we put them all into a dictionary, what Python say as a dictionary. So we control enter, and then we then create a concrete model. There's then the model, like a package of the linear programming. And then we defined the decision variable or the independent variable. So how many portion per meal, how many portion per item that we are going to eat per minute, in such a way that we want to, yeah, that's what we want to know, right? So if I want to eat some combinations of food that obey minimum numbers and also with minimum cost, what those foods are and then how many, right? So that's the decision variable. So we control enter. And then we also need to calculate the calorie, right? Because we define the calorie then, because we're going to do that, use it later. And then we define the objective functions. So this guy, where's that guy? So items times cost. So items times cost for everything, and then we sum it, right? So item one times cost one, and then the plus item objective function, and then we define that objective into yeah, a variable total cost, right? Because it is a variable. And then in this case, linear programming here, the sense is one, it's minimizing, right? And then we define the constraint. So it's basically this constraint. So items times carbohydrate should be larger than or equal to minimum carbohydrate. We define minimum carbohydrate over here. And then, yeah, items times carbohydrate content larger than minimum carbohydrate. This then minimum carbo constraint. So this is another constraint. There's another constraint. There's one constraint. And then this is then the predicted calorie, because we have now the predicted the model, right? So this guy, because we have updated our prediction, so we will then use this prediction. So I can use, I mean, to save time, I don't need to because we fat, we include the fat as well. So just use the old regression, right? But you know how to do this. So we just update this number, update that number, remove this guy, and then update this intercept. And then we call it like total calorie. And then we enter. And then see if you want to check if model is created well. And then this is then if you can read this. That means, like, for example, yeah, this is then the food index. Almonds, that's the first row. Where's that guy? Almonds, and then multiplied with, sorry, oh, these are all the sets. And then, so all of these sets, these are all the variables, how many, right? All zero still now. Objective functions. So 3.5, which is the price of almond. 3.5 times how many almonds that we want to eat. Right? Where was it? See? So that's this guy. Right. 3.5 plus 3.5 for the other almond, plus 5 for archer, and so on and so forth. Right? That's our objective functions. And we have our constraint, calorie constraint. Same thing, multiplied with the calorie for each item, but then larger than or equal to this number, the minimum, right? Um, and then for the fat as well, what's that guy? Carbo, carbo, oh, 500. And so on and so forth. Okay, so now we will call the solver, what I call it GLPK is the solver, and then we will then solve them, put it in the results. So we control enter, and then we put the results, as in this case, we get it's optimal. So that means we find the solution, and then what is then the total cost? Is 20. So that is then the total cost that we need to eat to obey, to fulfill the constraints over here. Where is that? Where is that thing? See, to eat minimum 500 carbohydrate, minimum 400 protein, minimum fat 100, maximum 1,000. We only need 20 ringgit, 20 ringgit. And then what are they? So it says, well, you can eat this milk 50 mils. Right? So you and here. So instead of spread it over different types of meals, it says, oh, no, 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 no. If you want to really minimize costs by obeying those constraints, you can only eat milk. Which in a way, okay. So you can multiply this 50 times the cost of this milk, and then you will get 20 cost, and then it fulfills. So this milk reduce fat, it fulfills, right? So it's not counterintuitive. It's just like numeric. So depending on the because this milk, it has all of this so it has fat, it has calories, it has carbohydrate, it has the protein. So if we eat or we drink this milk 50 portion, will fulfill our constraint. So that's basically what it is. And then if I want to see the others, example, I can also see this one. And then so everything. So there's no almond, no archer, no Atenas. And then we have milk is somewhere here. So we need to have 50 of this milk, right? So this is then the answer given to us by the linear programming. And then what is then the calorie? 5,000 calorie. Oh, that's too much, right? So, but nonetheless, if we combine all of these codes together, because I put all the codes in separately. So if you combine all of them, so to you, so we get, we print everything, we get this. So now, what if we limit the amount of calories? So 5,000 seems to be a lot, right? So let's maximum 4,000. I change the number from 5,000, from, I think calorie is, oh, I don't put any calorie maximum. So you can then do whatever you want. But then in this case, I put the max calorie, right? And then in this max calorie, we define another constraint. Calorie, add this calorie, right? Max calorie. Total calorie that we calculate from here, we calculate total calorie. It should be less than or equal to the max calorie. So if we do this, we get, okay, now it's 10, because many of these foods, well, it comes with a calorie, right? So we can say, okay, now 4,000 is our total calorie that we allow, and then to fulfill this 4,000 calorie, we then have to eat 11.8 of eggs, and then 29.9 of milk, like 30, 12, and then 29 of the same milk, right? Instead of 50. That's how we do this. And then we can also think, okay, now why do I have two milks? Right? I can also reduce this. And then in that sense, we can then create another constraint, and then we put, so this item, it should be 0. So we can do so, right? So we can add more and more and more constraints, but make sure by adding more constraints, I mean our solution space will become smaller, smaller, right? So say for example, if I say, okay, now 4,000 seems to be a lot as well. If I reduce it to like 3,000, and then and it says, well, I am now constrained too much. I cannot find any food that fulfill the minimum carbohydrate protein, but they have to be lower than 3,000 in their calorie. So it's invisible, right? Um, and then we can then, okay, now, 3,000, I mean 3,500 maybe. And then it's also still invisible. So okay, anyway, 4,000 it is. So this is then the amount. But we can also increase, right? If I want to have like minimum fat, I can have like okay, because we want to have like 800, we can do so, and then we'll have it. No, it's also like invisible. If I have like this guy, so I have now 4,000 calories increasing. So that's how we do the prescriptive analytics using the linear programming. And then this will then tell us, okay, if I want to minimize the cost, this is then the total cost. This is then what I should do, decision variables, right? So this is then, I think, the end of this a quick introduction to data analytics. We have covered the exploratory data analytics. We have covered the predictive analytics, and then lastly, we have covered quickly the prescriptive analytics, or the optimization part of stuff. So I think if there's no questions, then yeah, I think I can share with you the code. I think I will give this to Alif, right? And then he will then distribute to you because he has the everything. And then if we have two data sets given different excels, yeah. In this case, we have to just simply define it. Very good question. So we just simply define it. Where is that stuff again? Mana dia? One second, ya. One second. So we can say, okay, now I have the one file, right? So we get the file. So just simply get the file. So you can say, okay, this is my file with the training, and then create another my data underscore test, and then when we do this, where's that stuff? When we do this, we can say, okay, now here we define it. Okay, so my extract, extract. Okay, now I have it already separate, right? If you have it separate, so you don't need to do this anymore. It's just that when we do this, okay, so this is then from one Excel file, right? This is from the same Excel file, and then this then from the other Excel file. So we just simply defined the Excel file into these variables. So you can skip that sklearn stuff and then define them separately from here, for example. So this is then for my one Excel file. These are all the tests. So data numeric tests, right? So you can say this is data numeric test. And then from the other file, data numeric train. And then in this case, in this guy, so you can say, okay, I have this one. So data numeric test, sorry, data numeric train and then data numeric test. So as simple as that. Any other questions? Um, I think no more questions. We can if there's no more questions, any other questions? If there's no more questions, I think we can end this session here. And then for more for more training, I mean for in depth, I know it's very just what we need is practice, and then we can go in depth, and which we cannot do in this 1 hour session. So we can go in depth in a more elaborate training, so that we can then I can how call it we can then see each other's progress and performance, and then get you familiar with the tools, and then get you familiar with the concept of this descriptive analytics, predictive analytics, and then prescriptive analytics. Especially nowadays, uh, yeah, it's like I said in the beginning, our education system traditionally they are not fully equipped with these three aspects. So everyone will then learn these bits and pieces in some points in their life, if they are fortunate enough to go down this path, right? If not, then we will then have to independently seek for help. So I don't know if Alif is still there, or if I can just simply
Okay.
close the session.
No more question, eh? Okay. So thank you so much, Engineer Zulfan, for the presentation and the highly practical sharing. So we also extend our gratitude to all participants for your time and active engagement. And feel free to explore our training course at IEMTA website. Okay. So on behalf of
Yeah,
IEM Training Academy, we wish you continue success in your professional learning journey. Okay. Thank you so much for today and have a great day.
yeah. Thank you. Yeah, I
All
think
right. Thank you.
Alif and I we will then put this into one of the training materials which you can see
Okay.
in the website.
All right.
Thank you. Bye bye.
All right. Bye bye. Assalamualaikum.
Waalaikumsalam.